All right, good morning, everybody, to another Monday. So, just like if I remember, I had my transformed, let's say it like this, transformations of y equals x squared can lead to, when I simplify it, lead to, well, when I look at the transformation version, a x minus p squared plus q, and when I simplify it, I have the general form y equals ax squared plus bx plus c. Now, if I look at transformations, like the one I showed in the problem, of all these basic functions, x cubed, y equals x to the 4, and there's no limit on the powers of x, now they are going to create, after simplification, general form. Well, of course, the leading term, the highest power of x, depends on which one I started with, sure. But in general, let's suppose we work with y equals x to the n. Don't know which one. It could be any one of those. So my general form then is going to be the highest power is x to the n, and I'm going to have a number in front that I'll call a sub n. Then I could have another number as the coefficient of the next power down, and that can go all the way to the coefficient of x and just a number on its own called the constant term. This guy over here is called the leading term, and these are words that you should know already. The coefficient of that highest power of x is called the leading coefficient. And that's pretty much it. Oh, the degree, the highest power is called the degree. And this is called a polynomial. But they're built on these basic functions, right? Transformations made more complicated, and we can get our polynomial. So this is, in a sense, the simplest family of functions, where I have combinations of powers of x. Now, as I have different terms here in general, not just these basic transformations, I can have more variety in terms of going up and down and so on. The basic transformations give me a starting point, but there are more that is possible inside this family of polynomials. Okay, but still, in a sense, the simplest kind of function. All right, so I have my basic functions. That is the starting point for this family of, this large family of functions. Okay. Now, let me just see where I am so I don't miss anything. We said odd powers versus even powers, general form, and so on. Okay. So when I look at my basic function, transformed maybe, in some cases, well, in all the cases, the polynomial has a property. Yes, it could turn up and down and all kinds of things as the polynomial itself gets more complicated, but there's no end to the graph on either side. In the case of building on x to the 4, it's going to go up forever. I don't draw it very far, but if I go far to the left, there's going to be a graph way up here. It's just going to grow very quickly, but there's always going to be a y value for every x value. If I look at, where's this one? The odd powers, the shape is a little different, more general, it can have a little bit more curvature in it, but still it's defined for all x values. It's going to go, if I go far to the right and I'm looking for an x value, there is a y value. The graph is just a little bit too steep for me to draw. So I want to note this. Note that polynomial functions are defined for all values of x. Let's call them f of x. So I've named the input as x. For all x values, it's defined. And let's say here, the y value or y values grow in size, could be positive or negative, as the x values grow in size as well, positive or negative. If the x value grows in the positive direction, of course, then I'm going to the right. Then the graph is always going to go either down or up forever. It's never going to stop. So the size of the y value, the absolute value of the y value, is going to grow. It's just a question of, is it going to be negative or positive? If I go very far to the left, the x values grow in size, but negative. So there's a difference between the number and the size, absolute value of the number. I don't want to say the x values get smaller because I'll reserve that for being close to 0. They grow in size, but negative. So far to the left, the graph is going to continue forever. It's going to continue forever. The question is just up or down. The size of the y values will grow. Is it positive or negative? That's the only issue. I'm seeing a question in the chat. Does the leading coefficient include n? No, the leading coefficient is a number. But we run out of letters when there are too many powers of x. So instead of calling them a, b, c, d, e, and so on, we just use a with subscripts, but these are different numbers in front of the x. The leading coefficient is the number in front of the highest power of x. All right. Oops, keep doing that. Okay, so it's a feature, a main property of the polynomial that it goes on forever. So now we need to just get the words within this mathematical language clear. Mathematical words to describe this growing of the x and y values. And we, of course, do that by way of symbols. So if we say x grows in size, always positive. I'm trying to make the words in English as simple as possible so that we understand what we're saying. We're going to represent that by x, that's my variable name, then an arrow, and then infinity. And we will casually say x approaches infinity. But that is just a short way to represent the behavior of x values. It's a behavior that I'm trying to indicate. What am I what am I looking at for the x values? They're growing and they're always positive. 10, 100, 1,000, million, getting bigger and bigger positive. So on the x-axis, I'm going to the right. Okay. Then, if I go in the opposite direction, the x values grow in size. If I look at the absolute value, then the size of the number, but always negative, I'm going to indicate that with x, of course, my variable name. It's a behavior. That's where the arrow comes in. And then negative infinity to indicate that it's going in the opposite direction. And we sometimes say, or it's a little more casual, to say x approaches negative infinity. Well, I wouldn't say it's casual. That is how we say it, but it's not as if infinity is a number. Infinity is not a number, and it's just a direction for where the x values are going. So they're going far to the left. So when we say x approaches infinity or negative infinity, it doesn't mean it's a destination it can ever get to. It's more a behavior, a direction. So this arrow here that I'm using, it indicates behavior. And that is a very important word moving forward. I want to investigate how my polynomial, how my function behaves. Well, what has happened to the x values? Because depending on which side I'm going, the graph might look very different. So we can isolate this and just ask for this long-term behavior. So the arrow indicates behavior. The infinity means I'm never stopping. It's long-term behavior. There is no stopping. It's just a question of which direction do I want to go. All right. So let's look at something specific. Problem 1.12. Problem 112, number, which one do I want to do? Number 3. Yes. Okay, let's go there. Where is it? Where is it? Problem 112, show yourself. There you are. Okay, so when I'm looking at long-term behavior, because of the arrow, it's not equal to a number. Infinity to indicate long-term, I'm going forever in one direction or the other. We can also call that long-term behavior asymptotic behavior. And we'll elaborate on that word a little bit more. Right now, all we're meaning is long-term behavior. And you see here, I have a function. We're doing number 3. If x approaches infinity, meaning x grows in size indefinitely, forever, what is happening to this function? It's a polynomial, so let's write that down. So if x grows forever, x approaches infinity, then what is happening to my function? I'll just copy the function, x cubed minus 4x squared minus 4x minus 5. What is that approach? So let's call it y, so it's a little bit easier to refer to. Let y be this function. the name of this function. Okay, so now I want to know. I don't know what this graph looks like, but that's also not the question. The question is just, what is the long-term behavior to the right? The graph could go up and down, all kinds of things. Eventually, is it going up or is it going down? That's the question. I don't know what the ups and downs in the short term looks like. I'm only asking what happens in the long term. Being a polynomial, eventually it's going to go up forever. All the turning is done. It's going to go up forever, or it's going to go down forever. Which one is it and why? Okay, so that's the question. So now, in order for me to understand what determines the behavior of polynomials, I want to do my first question in the following way. So I'm going to write my function as the following. I'm going to take x cubed out as if it's a factor. Then I'm going to have to multiply with something minus something else, minus something else, minus something else, in order to get my original function back. When I multiply the x cubed in, I'm going to have to get x cubed minus 4x squared and so on back. Oh, stupid truck outside. Hopefully you can still hear me. So the very first term is going to have to be a 1, right? So when I multiply it in, I get x cubed back. The next one, I claim, is going to have to be 4 over x. So that when I multiply the x cubed by 4 over x, I get my 4. 1x at the top cancels with 1x at the bottom to leave 2 x's. And I'm going to have to multiply, I'm going to have the third one in the bracket 4 over x squared. So that I get my 4, and when I cancel the x's, I'm left with 1x. And the last one's going to then have to be 5 over x cubed. So that when I multiply it in, I'm left with just the 5. Okay, so I'm going to rewrite my function in this way, which is equivalent for large values of x. It's not exactly the same. I'm not writing y equals here specifically because the top function, my original polynomial, is defined at x equal to 0. While this new version is technically not. But it's the same for large values of x. I have to have fractions inside because when I multiply the x cubed back in, I have to get my original function. How am I going to get x cubed? Well, just x cubed times 1. How am I going to get an x squared if I have x cubed currently? There's going to have to be an x at the bottom to get rid of some x's and leave me with 2 x's. If I, for example, let me just make some space here. Let's erase this a little bit so I can just focus on one of them. My eraser is so small, so tiny. I can make it bigger, but I don't want to. Let's suppose I'm looking just at those two. Then I get x cubed, which is of course x cubed over 1, times, I'm going to put the negative, I don't care about the negative. The negative checks out. 4 over x is my claim. So I get my 4. I have 3 x's at the top, 1 x at the bottom, So one of those x's cancel with one of those, and I have two x's giving me 4x squared. I need one. I need an x at the bottom to get rid of some x's. So I need the fractions so that it simplifies back to my original function. It has to be fractions. There's no choice. Because I have fewer x's in the other terms. Okay, so let me get rid of that. Slow as it is, tiny eraser, you can do it. Almost there. Okay. And I'm only doing this for the first one, so I understand why polynomials do what they do. Okay? I need to understand. Otherwise, I can't adapt or modify to more complicated functions. Okay. So for large values of x, this function version is equivalent. Okay. So now the question is, what happens to the pieces as x gets really big? And the first one is a slower discussion. Once we get the hang of it, it's going to speed up a lot. So now the question is, what, not what, that's not the word. How do these, I'll call them pieces, that make up this function behave as x gets large? That is the question. Well, for that, I have to look at x cubed. Okay, so now I say if x approaches infinity, which is what we're investigating, then x cubed, let me not do x cubed yet. I'm going to do the fractions first. So I'll do 1 over x first. How does 1 over x, the fraction, behave when x, now the denominator, gets really big? How do I feel about that? Do I have a sense of what that fraction is doing? What is happening to that fraction? I can make a little table, perhaps. Let's make a little table of values x versus 1 over x. Now x is getting bigger, right? Let's go 1, 10, 100, 1,000, and so on. What happens to 1 over x? Well, x is 1. 1 over x is 1. When x is 10, 1 over x is 0.1. When x is 100, 1 over x is 0.01. 0.001. Which direction is this going? It's going to 0. So if x gets bigger, 1 over x gets really, really small. And the bigger x becomes, the closer 1 over x is to 0. But that is a key fundamental concept that you have to be okay with. Make a table. Play with some numbers. Make the numbers bigger. What happens to the fraction that I'm interested in? Get smaller, closer to 0. Is everyone happy with that? X gets bigger, and when that x is in the denominator, that is going to make a little fraction. So now, does it matter? I'll make it like this. That's 1. I want to make a list here. Does it matter if it's 4 over x? Does that affect the behavior at all? If x gets bigger, now x is as big as you can imagine, and then bigger. There is no limit. There's no end to x. Does it matter if I look at 4 over x instead of 1 over x? In terms of how it behaves, how that fraction behaves. Is it going to steer it into a different direction? It might slow it down initially, but when x blows up, the denominator is so inconceivably large that 4 doesn't make any impact. So it's still going to shrink down to 0. You're thinking, if you're not sure how big x is, it's bigger than anything you can even imagine. There's no end. Does it matter if I make it negative? I'm only interested in the size. The size is the only thing that matters right now. Does the size of that fraction change by having a negative in front of it? That is a question to you. Does the behavior change if I have a negative there? Okay, you say yes. Let's put a negative over here in my table. Then when x is 1, negative 1 over x becomes negative, 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 negative. What happens to the size of that fraction? It's still shrinking. It's still going to 0. Yes, from the negative side, but it's still heading in the same direction. It's the direction, it's the behavior of the fraction, and really only for now, in terms of its size, is the only thing that matters. Later on, we'll update that, but right now we don't care. We only care about the size of the number. So this fraction here is going to shrink down to 0. It's not going to be 0. Notice these are arrows. These are not equal signs, ever. Because I will always have a little fraction. That little fraction is never going to be equal to 0. But it's going to be so immensely small, it behaves the same. Now let's loop over here, make some more. What happens to 1 over x squared when x gets really big? Does anything really change that behavior of that fraction? If anything now, my denominator is even bigger because I have x times x in the denominator and the numerator is still 1. So if I make my little table, it's just going to go to 0 faster. Now, this arrow doesn't indicate speed. It's just which direction is it going, how does it behave. So is everyone happy that 1 over x squared will get smaller and smaller to 0, really as close as I want, if x is just big enough? Is everyone happy with that? Now, these are key things that are going to come up over and over and over. We have to be super happy with it. How the behavior of one influences the behavior of another because they are related. Does it matter if I have a negative 4 in front of it? I see no one's answering my questions anymore. All right, maybe because it's obvious. It does not. They're all going to shrink down to 0. Same for more x's in the denominator. It all shrinks down to 0. Okay, so what's really left here is an x cubed, and inside the bracket, essentially, is left 1. Because what I'm subtracting is so incredibly small, they have no significant impact on the size of this number anymore, on this y value. So let's write that out. Let's write that out. We say that as x approaches infinity, meaning x grows bigger and bigger in size, then I'll say it then here. Y behaves the same as x cubed times 1, because those are the only things that are left. Stupid line. Sorry, I'm pressing, but there's a delay. I have some lag issues because of D2L. And I'm not bad-mouthing D2L. I know it's D2L. In my version up here of the function, everything shrinks down to 0 except the x cubed and the 1. They don't. So if x is big enough, and this is a key sentence here, if x is big enough, then my function y behaves the same as x cubed times 1, and the 1 doesn't actually matter. So that means that if I look at my x cubed function, where is it? It's over here. That in the middle, it could be very different, up and down, all kinds of things. But if I just go far enough, eventually it's going to follow that template x cubed graph. In the middle, many other ups and downs could be happening, and probably are happening. But eventually, when they're all done, it's going to copy and mirror what this x cubed graph is doing. Long-term behavior. I don't know when it happens. It could take a very long time to really get close to this. But if I wait long enough, I go far enough to the right, it's going to almost sit exactly on this x cubed graph if I just go far enough. So now what I've done is I've taken a complicated function, the one up here, x cubed minus 4x squared and minus 4x minus 5 with ups and downs and all kinds of stuff. And if I'm asking for the long-term behavior, the long-term behavior is the same as x cubed. And because that is a basic function, I know what that does. This is just x cubed, and x cubed gets bigger and bigger as x gets bigger and bigger. Therefore, I can conclude that my original polynomial that was more complicated also gets bigger and bigger in size as x gets bigger. I don't know what's happening in the middle. All I know is eventually the y values will blow up as well. If x is big enough, then, or bigger and bigger, then these function values, these y values, will get bigger and bigger. Now, this was a whole thing because it's our first example. It doesn't always have to be a whole thing like this. This is going to apply to all functions, but if the fundamental type of the function is different, like a square root function and so on, then sometimes we need to just alter this explanation a little bit. But essentially, we can ask this long-term behavior question about all the functions, of course. Silly line. Let me just scroll back down. It's so nice when you press a button and nothing happens. I'm looking for my little hand. Come on, scrolly. So now my question is, how is this x cubed times 1 related to the original function? The original function, x cubed times 1, is exactly the leading term. Yeah, I would say don't worry about all the other functions right now. We're building up from the easy ones, and they are polynomials for now. We're going to get to all of them. Square roots are a little hard to talk about right now. One thing at a time. This leading term has a 1 in front of it, and it's x cubed. And if I take another function, the other one I want to do is number 2, for example. I see a different polynomial. If I do the same thing, what's going to be left is a -5 and then x to the 4. Let's see that. I need to make a new page. I have 2 minutes left, so that should be totally fine. That is exactly our example when a is a little bigger. Or not bigger, just different maybe. Problem 1.12, not 9. Number 2. So there we have whatever x does. Really, I really don't care that much. It's big in size. I have a polynomial. That polynomial is different and complicated, and I don't know what it looks like. And it's going to go up and down and do all kinds of crazy stuff. Well, I don't know what it is, but I'm only asking for the long-term behavior. So if I now do the same thing and write this y as taking out the highest power of x, you can take your time to verify. I'm going to get -5, not a comma. -5, I'm going to get minus 3 over x plus 1 over x squared minus 10 over x to the 4 with the same argument. All of these are going to shrink down so close to 0 I can't even tell them apart. The only things that are left are exactly the things in the leading term. So again, my function, I'll call it y, behaves the same as x to the 4 times -5, which is the leading term. And this is a key property of the polynomial, that if I ask a long-term behavior question, then the polynomial behaves the same as its leading term. The other terms make ups and downs in the short term. Long term, they all fall away. This is what these arrows going to 0 essentially say. In comparison to the leading term, when x is big enough in size, these other terms are negligible. They're so small. So when I look at a polynomial and the long-term question, I only need to look at what its leading term does. And that leading term is a basic transformation of a function I should know. So now we know what -5x to the 4 would do. Because it's just a basic transformation. I flip it horizontally, I stretch it a little bit, it's going to look like that, right? So long term, x, I'm now looking at to the far left. So I'm looking over here, far left, as x approaches -infinity. I shouldn't call it y. -5x to the 4 approaches -infinity. Because it's a transformation of my basic graph, I can easily read it off. And my original polynomial behaves the same as this basic function. So therefore I can go up and say that this question mark in the original question has to be a -infinity. Because that is how the leading term behaves. Couple of transformations on a basic function, so I can very easily identify how that behaves, and that long term determines the behavior of the whole polynomial. All right, so that's the key concept here. Long-term behavior of a polynomial is completely determined by its leading term. And that leading term is a very simple function. It's a simple transformation on a simple power of x that's easy to understand. And yet the whole polynomial is following that simple function. After all, the middle ups and downs are done. Only long term do we say that, of course. Okay, so we're going to continue this discussion about long-term behavior tomorrow. The only key thing here is now, how do I evaluate the long-term behavior of a polynomial? So you can look at problems like in 1.12, 1, 2, 3, 4, 5, 6. if you want to practice. Okay, x goes far to the left. How does this polynomial behave? How does this polynomial behave? Just to get used to only looking at the leading term. The rest of this, it doesn't matter. It's completely irrelevant for long-term behavior. Okay, we went a little over, but that's okay. Any questions or thoughts at this stage? We will also continue this tomorrow because we're still talking about polynomials tomorrow. Question 7 is for tomorrow. I have to talk about that kind of function. It's not a polynomial anymore, but it is built on a polynomial. It's in the same section. We just need to make sure and see what little adjustments we need to make to help us understand the behavior of fractions of polynomials. So we need a little more time, and we'll do that tomorrow.